Good morning. Hello. Hi.
Good
Good
morning.
morning. Good morning to all. It's so always so good to join you guys in the morning. Good morning, Owen. Hi, Nathan and Brian. Good morning to you. Um, Let me arrange my screens just so I could see this. Good morning, Robin and Sanjita and Saja. Also, good morning. Thanks for joining me, guys, at 10 a.m. Good morning, Esmeralda and Isla. Also. Oh, and I see we have a whole bunch of people joining us now too. Good morning, Andrea. Hi, Bafar. Good morning. I hope you're all doing well. It's Wednesday. We're really close to finishing this week off, and good news, everyone. I think Monday's a holiday. Yeah, I think so. We'll triple check, but I think it is. Sanja says yes. I think it's MLK Day. Yeah.
That's great. That's great.
It really is. And let me give you guys like a just a some a funny story. It's not that funny. It's not a story either. Okay, anyways. So normally, good morning, Gary. So normally, every time I teach this summer session, you know, in winter you get MLK Day, and in session one in the summer you get 4th of July, and then session two there's no holiday. And I was so upset that there was no holiday, that we need that five during that 5 weeks we need a break. So I made a holiday and during session two I gave my class and my
Aww.
a day off. Yeah, because it's needed. Like, what's wrong with these people? They get us used to like having a day off in the middle of the session. Like we need that. So yeah, I think we have Monday off. I'll remind you of that tomorrow. um yeah, and I hope you do take it off. Yes, good morning to Daniela. Good morning to Owen. I'll answer your question in a second too. And Randy, 6 hours on that Sudoku. That's a good effort. That's a
Yeah.
good, yeah, that'll build that thick skin that you need, you know?
I
Yeah.
found a method for the beginner one. Like it's a method that works all the time,
Oh,
and
okay.
you never make it. You don't have to make one single mistake on it if you use the method. But I don't think it works on the other one.
Ah, I see.
It
Well,
only works on the beginner one because when there's more than like a bunch of things empty, it doesn't work.
yeah, that's exactly right. And that's when you just start to make up your own methods and see what works for you. So, yeah, I'm glad you guys now like Sudoku, or at least you're familiar
Oh,
with
I
it.
didn't say I wouldn't go that far.
Keon says he now loves it. So it really depends. And again, in engineering and physics, you're going to come across so many problems that are seemingly impossible. Truly, you're going to say, I don't know how to solve this. There's no answer. And you're going to fight the book on it, fight me on it. But there's always a solution. And sometimes you just have to step away, come back the next day and have, a whole new thought process. Sometimes you'll find the solution while you're like taking a shower or something. Something will pop up in your head.
I would definitely do it if I were stranded on an island with no entertainment or to kill a lot of time. But I don't know if I'd, do it if I had anything else to do.
It's actually funny you say that because um, when I mean, I've always been into Sudoku, but when I got into like the other versions of Sudoku, like the adding ones, the other one that I like is called Kakuro. I was in Thailand and I was traveling from city to city for like, I don't know, I was doing work over there, and there was moments when I didn't have internet and I literally was just waiting for the next thing to do, right? And so I
Yeah.
had this Kakuro book, and every time I'd finish a puzzle, I would write exactly where I was and what I was doing at that moment. And almost every single puzzle is some different city, either in a hotel room, in a car, in a bus, just or in a boat, just waiting around for like, you know. But now you find other ways, I guess, to entertain yourself too. Yeah, yeah, I love Thailand. I lived there for 6 months. Um, at the towards the end of my undergrad, I actually extended my undergrad just so that I could go do research in Thailand, and so it was 100% worth it. Yeah. Um,
Did you have fun with food?
Oh my gosh, yes. And for yeah, I tried everything before I went to Thailand. Um I don't like, okay, nobody get upset here, but I don't like curry. Um and I went to Thailand thinking I'm gonna try every single thing they give me, and I did. I tried every single curry that they gave me. I Everything that they gave me that I didn't like, I always tried it. Now I know a specific type of curry that I could eat, a peanut based curry. And so now that's what I order. But yeah, my favorite food in Thailand that I ate every day at the university cafeteria was a basil chicken, like ground chicken with basil. That's all I ate. Yes, panang curry is my favorite. Um, Okay, lots of questions, but let me go back to Owen's first question. Are you going to teach Physics 102 over the summer? That's the normal schedule of what I teach, and I'm I it hasn't come out yet, and I don't know yet. I don't know yet. As soon as I know, I will tell you. Um, Probably in a few weeks we'll know. So as soon as I know, I will tell you. I think that was yeah, we do have Monday off, Luis. So, yeah, I'll remind you guys too. Um, oh, I went all over the country in Thailand. Go everywhere, to the south, to the north, the west, the east. I like the north of Thailand a lot. It's I don't want to say quieter, but there's a lot of nature to see. There's a lot of nature to see all over Thailand, but very nice. What was I researching? Oh, materials. I was looking at um, stainless steel materials and how they were rusting. So looking at different oxidizing methods. Um, yeah, because stainless steel shouldn't rust, right? But when something has too much salt in it, it ends up rusting. And so I was, yeah, doing a lot of polishing and imaging of things and causing it to rust in the lab to see why these materials were actually rusting. It was pretty cool. It was about like maybe 12 plus weeks of lab work. Um, yeah, and then a lot of writing and stuff to do. Yeah, good times. And one day again, we will all get to travel. I hope, near and far, right? Any way you can. Yeah, I was just looking at tickets this morning for the Huntington Library. If anyone's been there, I love going to walk at different gardens, and you know, I need to find somewhere to walk that also gives me the sun. So maybe that's what I'll do. Yeah, it is so pretty there. Yeah, field trip for everyone, right? Just like engineering 101. We had a field trip to the Trade Tech parking lot to pick up materials for the wood. And I got to meet Keon in person. That was cool. And like maybe 25 other students, which was so funny because when everyone came to pick up their materials, hardly anyone overlapped with the next person. So it really worked out. Yeah, hopefully soon, guys. Things will. I hope. I'm very hopeful. I stay in the positive. So
My I work at the school, and my boss is now telling me that we won't be back until next spring.
yeah. So
Yeah.
officially, that's the district officially is saying that they're also going to be online in the fall, but they add that sentence, right, that as things change, anything can change too. So yeah, the other thing, I'm starting my slideshow, by the way, just while I'm talking. The other thing is we are a huge district, so it's not as easy for us to open as like a private school like USC that can they can do whatever they want and they govern themselves. So that's not the case for our 9 campus district. So
Oh yeah.
yeah, we have to do what works for everyone. And I will say that I think um, trade is working very hard on this because we have so many hands-on programs. Yeah, and in the sciences, you might see some in-class labs perhaps. Oh, and Luis is telling us at CSUN we will resume classes in the summer in person. I was told by a professor. Wow. Oh, and Boston is opened up, but have so many COVID cases here we can't even compare. Yeah, Yeah, and then LA is very big on, we have so many testing sites, which means our numbers, we have more data. So, although I feel very safe in general because I take care of myself. But yeah, in general, we, I don't know, LA is there's a lot of people here, and yeah, you got to keep a track of the masses, and that's always hard.
Can I ask a question to the class and to you, I guess?
Sure.
Upon doing the problem set 4 from last night's homework, basically, was anybody able to just like go through it and not have to look at a solution, just like to do it all on their own without any assistance?
Not me.
Okay, that makes me feel better.
So I'll also say this, and I've been meaning to say this for this class because we are, remember, we're in an accelerated schedule, and this is Physics 101. So typically, this is an many of you might have when this class is taken in the fall. Usually, it might be the first class for a lot of you in college. Period. Or at least in the sciences. And so this class, along with calculus, is always going to pose a challenge. The big difference between your college classes and anything you do in high school is that flip of how much work has to be done at home versus in class. And you go from doing 80% of the work in the classroom in high school and 20% at home. That completely flips in college. Now you're doing 80% of the work on your own, and 20% of the learning happens in the classroom. And so that's an adjustment. And in physics and calculus, when these are your first major science classes, that's an even bigger adjustment. So that's why I also say solutions are not, they're, use them. Solutions are there to help you, to guide you when you don't have immediate access to someone that can walk you through it, right?
You
So,
don't think they're like a crutch at all, right? Like,
I don't think, I truly do not think they're a crutch as long as you're honest with yourself of how much you know and how much you're depending on it.
like
Um,
sometimes I will say like I can't understand the solution, and that's when I have to have help. But like for the most part, understand like as I figure out what they're explaining in the justifications, that like is teaching me. But
yeah.
like I feel bad that I have to look at that because I feel like maybe we were already taught it in class.
Yeah, well, I'll say never try hard not to feel bad about it. Just know that that's part of your process. And if a solution doesn't match the way that you would write it, but the solution is still pretty much there, that's okay. It becomes a matter of wording, right? And a matter of how the textbook wants it presented for a physics class. And in general, you want to be able to adjust and pivot for whatever class you're in, right? If you're in a
Yeah.
physics class, adjust it to a physics. Um, my goal is not to, have you guys learn everything as the best physicist that you can be. My goal is to have you be able to use this stuff in your future classes, right? So you need to be able to adjust, and I'm going to constantly tell you, but think about how you would use this practically. How will you
Yeah.
would use this in further classes. So I truly don't think they're a crutch, but you have to be honest with yourself how much you depend on them and how much you rely on them. And I do think using them as a guide help a lot because once I see it once or twice, then I can do it on my own the third or fourth time. That's how I use them.
Like
Um,
something that stuck with me from the solution that I was looking at for a problem last night was that like I was like they didn't explain that like Vx at final was the same as Vxi. Like I solved for Vxi, but I didn't solve for Vxf, and by the end I needed Vxf, but then I was like, oh, because there's no acceleration in the x direction, Vxf is the same as Vxi.
yeah, and
And so
and
that like hit me and stuck with me, and I think I'll always remember that.
that's good because that was a test question last semester. So, and it's just good to know that.
And it doesn't like explain it, in the solution. So figuring that like logically, is figuring that out.
that's why I emphasize it. It bothers me so much when they don't explain things. If someone reminds me at the end of class, I'll put up the physics website that I like, and I'm sure you guys have seen it. It's the Libre Physics Libre Text website.
Oh yeah.
Man, that one does everything in detail. So whenever a step is skipped in the book and I can't catch it, usually I can catch them. But when I can't catch it and I'm just frustrated that I need to figure out where this came from, I go to that website and I read that, and then I usually see the math there. And also, yeah, Noah and Daniela put some really good tips in the chat. Daniela uses other books, and yeah, use the book that speaks to you. I like our book because of the visuals, but I don't care for their wording. And so using the book for so many semesters, I've learned their language to translate it to you guys, right? But it really can be a lot about language sometimes. So really use what speaks to you. Noah says, yeah, there's always different ways to approach a problem, which sometimes makes it hard to understand in the beginning topics. And then Keon, I realize you can get past the paywall for the later solutions using Chrome's incognito mode. All right. And I'll say too, sometimes it's just so much faster to look up a solution than to like
Struggle incorrectly through a problem 4 times.
4 times. Yeah. By the third time, if you're truly not getting it, use the solution. And what I suggest is to write down a step-by-step process of what the solution did so that you can then little by little make that your own guide of solving a problem, right? Um, so yes, if you guys feel challenged, good. That means you're going to get better. That means you're growing. That means you're going to surpass whatever level you came into this class with. And that's what you want because all of your classes later will, start to build on each other. So um, definitely get comfortable with being uncomfortable.
How do you like look at a problem and know that you're going to be solving it for the variables rather than for a number? Like like last night, some of those
Yeah,
problems, like
yeah.
they just say, but like I didn't know that, and so I would put in 9.8, and then I'd get the wrong answer because
Yeah,
I would think you'd put all the numbers you can in.
yeah, and I see some people agreeing with you through the private chat with me and through just the videos. Yeah, sometimes you don't know, and if that doesn't match the solution, so first, how do you know? Usually, there's clues of saying, anytime later at any position. What is the motion, like sometimes it'll say total motion and then you just solve for an equation that represents that. Sometimes you're just not given enough information to get an actual value, and that's then the clue that you can't go any further. That's as far as you can go. um, and so if you get to the point where you just plug in numbers, just to get an estimation, that's okay. Or if you plug in numbers and it doesn't match exactly what the problem should be, um, like if you put in 9.8, but they showed it as G, that's okay. Both answers are correct. Yeah, both answers are correct. Yeah, okay. So more tips also in the chat. So that's great. Use everything you can because this is it. Ultimately, it really is about survival, right? Like how are you gonna get by? Yeah. Um, so today our goal is to get through um, most of chapter 5, and even given our time right now, I think we can do it. I think we can get to the slide that I want to get to, and if we don't, we have enough time tomorrow, so we'll be okay. um, and now we're going to also, to be clear, in case you're looking at the syllabus, we're not going to do chapter 6 formally. We're going to put parts of chapter 6 kind of scattered throughout. And so you already saw a little bit of circular motion, and you'll see much more when we get to the chapter on torque. So this week we are only going to do chapters 4 and 5, and the exam will only be based on chapters um, 4 and 5 and what you see in class today. So let us start chapter 5. So up until this point, believe it or not, everything we've done is to describe motion. Chapter 5 will now tell us what is the physics cause of motion. So you see everyone on the screen. Let's say we've all done this maybe, I don't know, in middle school, high school, at a family event somewhere, and you've tossed an egg to someone. The egg is not hard boiled. It's a raw egg. And as you catch the egg, you move your hands backwards, right? Why do we do this?
Or to give it like a cushion to slow it down slowly rather than quickly to make it less abrupt.
Okay, to cush it down, to give it a cushion. Guys, I
To
got.
like increase the time interval over which it decreases its speed.
I'm gonna go with the first thing you said, just because I'm.
Okay.
Hold on, give me a second. It's probably correct. My laptop just started overheating, so if anything happens, I'll be back. If I freeze or get kicked out, just hold tight. I will be back. Hopefully it'll stop soon. Okay, so the first thing you said was to give it a cushion to slow it down. So the point is we don't want it to break, right? And you don't want it to have that huge impact, that feeling. And so we do what Randy says. We slow it down. We kind of move our hands with it, right? And when we're doing that, you're really doing exactly just that. You're trying to slow it down. And now with everything we've learned in chapter 4, we can apply the idea of slowing something down to a physical meaning of reducing that acceleration, right? Slowing down
So
the motion of velocity.
so like if you make the time over which the acceleration happens larger uh then the acceleration is less,
Yes.
or
So
the if the velocity reducing is over a bigger time, then it's less acceleration.
yeah, so then you're slowing things down precisely. And so what we want to do now is take a step back, and instead of just being able to describe the motion of something using our kinematic equations, we are going to transition from the kinematics point of view to then studying the dynamics, which is things that are in motion, but what is it that causes that motion? And we're going to see that chapter 5 is all about force, and force is the thing that causes a change in motion, a change in motion. And again, up until now, everything we've done is describe the motion. We can find the final position, the final velocity, the initial velocity, the acceleration, but we haven't talked about what is it that causes that motion. And so that's what we're going to do in this chapter. And we're going to start that with Newton's laws of motion that really govern all of motion from very little to very, very large. So let's start, as we always do, by starting with a reference frame of some sort, almost like creating an origin, right? So Newton's, this is our first law, which is this first law in inertial frames. Sometimes the inertial frames part is considered like the zeroth law, but we'll start with just calling it the inertial frames part. Okay, if an object does not interact with any other object, it is possible to identify a reference frame in which the object has zero acceleration. This reference frame that we identify is a reference frame that we choose. And by choosing this reference frame where an object could have zero acceleration, all we're allowing ourselves to do is say that although an object appears to not be in motion, it can be in motion. And the biggest, and so this is called an inertial frame of reference. So you can create a frame of reference in which you're not moving to you in the frame of reference, but to someone else who's looking at you from a different frame of reference, they could see you moving. Now, this might sound confusing to begin with, but it's happening around us at all times. Our best example for this is our planet Earth, right? Yeah. Yeah. Oh, yes. And Luis has a great example, like someone standing on a train. Absolutely. So, this best approximation for the inertial frame of reference is Earth. Earth is that type of reference frame. Earth is always moving with some constant velocity, right? And this constant velocity that's relative to some distant stars. So we can see distant stars in space, and we can see them in the same part in space always. And to us, they look like they're not moving, but in fact, they are moving, right? Um, in this frame of reference, Earth, Earth has zero acceleration, right? So here, our frame of reference, this is our origin, and in this place, Earth has a zero acceleration. And we don't feel Earth accelerating, of course, even though we know that Earth is accelerating because we are in the inertial frame too. Yes, keeping snakes on a plane too, or anything that will not be poisonous and bite you on a plane, can also act that way. So imagine like when you're on a plane and you're standing still, right? When you're on a plane and you're standing still, you can call your frame of reference an inertial frame of reference because you can say, I'm not moving. But someone on Earth looking at the plane flying over you can absolutely see the plane moving and you moving too, really
Isn't
fast.
it interesting that like on a if you're that in movies like when they're on a roof and they jump, they go forward and backward, but like when you're inside the plane and you jump inside the train and you jump, it doesn't you don't move.
Yeah, isn't that, man? If you want to think about that some more, you're gonna love learning about theory of relativity in Physics 103. Usually, when I taught it this summer, and we're supposed to spend one day on it. It was so fun. Everyone got so into it that we spent the entire week. I just said, F it. We're gonna do the entire week theory of relativity because there are so many of these scenarios. Yes, Luis, like throwing a ball up from a moving car. It's amazing, and this is the foundation of this inertial frame of reference. So as long as you know that this exists, right? This is kind of our zeroth law. Yeah, we can call it kind of our zeroth law. And it's funny because before scientists were really studying this, the opposite was was thought, right? Around the 1600s, so not too long ago, 400 years or so ago, people believed that the actual natural state of objects was a state of rest. And because of Galileo and many of his experiments, this was proven to be wrong, that the actual natural state of an object was to be in motion unless something came and stopped it, right? So the idea before this was that a moving object would eventually stop moving just on its own because the natural state was to be in rest. It turns out this was not true. Galileo did a lot of experiments with the Leaning Tower of Pisa and with the incline once he was under house arrest. And he finally concluded that an object actually will resist changes in its motion. So it will remain in its natural motion until something wants to act on it, right? And so this is officially now our first law of motion given to us by Newton. In the absence of external forces and when viewed from an inertial reference frame, an object at rest will remain at rest and an object in motion will continue in motion with a constant velocity, that is, with a constant speed in a straight line. So let's be super clear about what this is saying. An object in motion continues in motion. The motion that they are referring to is a constant velocity, not an acceleration, but a velocity, because a change in velocity is then an acceleration, right? So an object at rest will stay at rest, and an object in motion will continue in motion unless an external force comes and acts on it. Something has to change that, right? So when no force acts on an object, the acceleration of the object will be zero. No force is acting on the object, the acceleration of the object is zero, but the velocity can still be some number, right? It can still be 5 mph, which means that we are still in motion. Even though no force is acting on us, even though we have zero acceleration, we still have a velocity. And then now we can define force as that which causes a change in motion, a change in motion. So we know that a change in motion over time is equal to acceleration. So this should bring up some instinct that the force is somehow going to be proportional to acceleration. Okay, let's try this question and let's try it on the quicker side. Which of the following statements is correct? It is possible for an object to have motion in the absence of forces on the object. It is possible to have forces on an object in the absence of motion of the object. A nor B. or A and B?
A and B.
Okay, we have a A and B. Can I get like a two, three more? Oh, okay, I have two more from Nathan and Bradley and Luis that also agree with Randy and are saying D, both A and B. Let's prove it, right? As long as it's, justified, right? Is it possible for an object to have motion in the absence of forces on the object? So we just did this one, right? Having motion means some velocity, some change in position over time. Can you have velocity without having a force acting on you? According to Newton's first law, yeah, you can stay in motion and continue in motion, in that same motion, if no external forces act on you. Now, the second one, it is possible to have forces on an object in the absence of motion of the object. Can
I'm sitting
anyone,
down and I don't have any motion.
huh?
I'm sitting down because of gravity, but I'm not moving.
Perfect example. Perfect example. Yeah. So I was going to ask for an example. Yes, and then Owen says it one more time. Its net force is zero. Yeah. So can you have an object a forces acting on an object with no motion of the object? Randy is sitting. You guys are all sitting right now. You are not moving, but you have many forces acting on you. And if you don't believe that, you can think about that you are not falling through to the center of Earth at this very moment because you have a normal force acting back up at you that is countering the gravity force that's acting down on you. So that keeps you, yeah, the net force is zero. And Owen, you had a comment earlier, but you can't have acceleration with no forces. You can't have acceleration with no force. So no acceleration.
But you can have velocity.
With no forces. You can't have acceleration with no forces. Like you need forces to accelerate. Yeah, but you could also have forces and have an acceleration equal to zero. That's what this is saying. Oh, and that's what you said afterwards, the net force. The sum of all the forces can equal zero, but that means that there are forces in there. Yeah, absolutely right. Okay, yeah, our answer is D. Good work here, guys. Okay, so when we think about an object that's accelerating and the forces, we kind of think, oh, they're proportional, right? If you push something really hard, it's going to move. If you push something doubly as hard, it should move twice as fast. What is it? What is the thing that might be the factor though? Like, are we going to use this? Is like is a cement block and a styrofoam box, are they going to move the same way?
No.
No, right? And the defining factor of those two objects is the mass, right? So now we come into, we can complete our definition of the forces by also bringing in the idea of a mass and how a mass plays a role in physics. So I'll ask all of you, which would you rather catch if being thrown at you at the same speed? Would you rather catch a bowling ball or a basketball? If both
a bowling pin.
That's not an option, Randy. Bowling ball. Bowling ball or a basketball. Yeah, everyone will say basketball, and Jose says depends on speed. But remember what I just said: the speed is the same for both throws. So if they're both being thrown the same, either way, you have to prefer one over the other, even if the speed is lower or not. Keon, which would you like to have thrown at you, a basketball or a bowling ball?
Well, I'm trying to buff up, so no, I'm kidding. I'll take the basketball.
Okay, so
And acceleration.
so you're trying to, yeah, you want to buff up, so you're going to take on the challenge of the bowling ball. So we have many answers for basketball. We have one for the bowling pin and one for the bowling ball. Yeah, so many of you say basketball, and this all depends on the mass, right? How is the way that each accelerates depends on the mass. And so the bowling ball we see is much more resistant to the changes in velocity than a basketball. A basketball can change its velocity very easily. It does not resist a change in its motion. The basketball does resist a change in its motion. It's harder to throw. The word harder tells us there's resistance there. Now, this brings us to our formal definition of physics, mass, not the chemistry definition, which is also correct, right? We said all of the matter that makes up an element is its mass. Now we say that mass is a property that specifies how much resistance an object exhibits to changes in its velocity. And we just want to think about how is an object going to change its motion? Is it going to resist it or not? A basketball has a low resistance. I'm just going to call it R, a low resistance, and so it has a smaller mass. A bowling ball has a higher resistance to a change in its motion, and so it has a higher mass. And so we see that when we talk about these changes in motion, a change in motion is the velocity changing. The velocity changing is the acceleration. So now we can formally apply this to Newton's second law, which is equivalent to our big kahuna equation in kinematics. This is the mother of them all, Newton's second law, my favorite. Okay, so Newton's second law will tell us what happens when an object, when there's forces acting on this object. So let's say we have an object. Notice that this object is only being identified by its mass. Of course, we draw it as like a block or a dot or something, but the mass is what identifies this object and its motion. Now, imagine if you're pushing this block of mass m across some frictionless horizontal surface. We say frictionless so that, we let go of all the small details in the problem that aren't going to affect the force right now. And so we push it. So this is some force. Notice that the force is a vector. And when we say the word pushing, we can call this an applied force, and we can put a small APP here, applied. And notice again, it is a vector. And so the vector that represents the direction and the magnitude of this force is this arrow that you see here. Okay, so imagine if we now push this vector, right? As we're pushing this vector, let me move my chat box. As we push this vector, as we push this block, we're going to cause the block to accelerate, right? The horizontal force on the block will move the block with some acceleration of A. Okay. If we were to apply twice the force on this block, we would probably get twice the acceleration. So mathematically, that means that the magnitude of the acceleration is proportional to the force. Now, you guys tell me. We talked again about the bowling ball and the basketball, but what about a heavy box? Is it easy or hard to move a heavy box? Easy or hard to move a heavy box?
What's that relative to, like, as opposed to a light box?
Yes.
Oh, then it's harder to move a heavy box?
Yeah, it's much harder. So they are not proportional to each other in this sense. In fact, they are going to be inversely proportional. As you accelerate an object, it will accelerate at a higher rate if it has a lower mass. If an object has a higher mass, it's going to accelerate at a lower rate because it's harder to move. Amir says, do you even lift? Yeah. And so mathematically, this relationship is then inversely proportional, right? So the acceleration is proportional to 1 over the mass. And let's just do this math out to make sure we all agree.
So acceleration.
So let me put an example in here. Let's say the mass is 10 kilograms. We would get 1 over 10, and this is equivalent to an acceleration of 0.1. This is, let's say, small. Now let's do something much larger, 1 over 100.
Well, isn't that a smaller box then?
No, a smaller box.
Oh, I see what you're saying.
So 0.01. So notice that the acceleration for here we have a larger mass. Oh no, that's a smaller mass. But I think you guys, I hope you see where I'm going with my arrows here.
Yeah, that's what I was saying.
Yeah. Okay. So let's do them in blue. We have a smaller mass will produce a larger acceleration, and a larger mass will produce a smaller acceleration. Do we see that relationship mathematically too? And it makes sense, right? A larger mass is going to be harder to accelerate. A smaller mass is going to be easier to accelerate. Okay, I see the thumbs up. Thanks, Owen. So notice that these two are both true, and they're both related to acceleration. So we could say something like this, right? We could combine the force and the 1 over mass, force times 1 over mass, and say that that is true. And we'll bring that over to the next slide. And here it is, guys, Newton's second law. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Yes, and before says it again, acceleration has the reverse relation to mass. That's right. And so this is the exact definition. And notice, we are defining the change in motion in terms of force and mass. Now, this is the definition. This is the Newton's second law of motion, but probably not what you guys are used to seeing. Let's reword it to focus on forces, right? The acceleration of any object will always be due to all of the forces that are acting on it. If several forces are acting on it, it will accelerate based on every single one of those forces added together. Like a hockey puck, right? A hockey puck will have several hockey players hit it at once, and the puck, the single object puck, will accelerate due to the force from each one of those hockey pucks hitting it at once. And so there are several ways to say this. We can say the net force. The net force can also be the total force. It could be the resultant force, like the sum of vectors, or it could be the unbalanced force. This isn't very commonly used, but think about the unbalanced force as, what is the remaining out of all the numbers? What is the positive value left, or what is the value that's left after they cancel out? Like 5 plus -5 plus 3. The unbalanced force is the 3, right? Because the 5 and -5 cancel out. So this net force or total force here is the vector sum of all the forces acting on the object. So let us reword this in terms of the force. Many forces may be acting on an object, but only one acceleration of the object. Let's rework that equation from the last slide. And now you hopefully see it as what, if you've ever seen this equation or heard it, F equals ma, this is how we're used to seeing it. Newton's second law is the total force. The sum of all the forces is equivalent or equal to the mass times the acceleration of the object. Notice we have vectors. And so what does this mean? As soon as we know we have vectors, we know that we can resolve this into its x, y, and z components. And here it is written in x, y, and z components. And let me be clear that this sum of forces, although it's one symbol, there can be several forces here. So you can have F applied plus force of gravity plus some other random force, and all of these added together will equal the mass and acceleration of one object, how one object is accelerating. So this is the sum of. And so anytime we start any one of these problems, and usually from now on, all of Physics 101 and 102, we'll talk about forces. I will always start off with Newton's second law. I will write at the top, Newton's second law. And you can start with F equals ma. Or if the problem already is obvious to you that it's in 2 dimensions, you can start with the sum of the forces in the x equals max. And then we'll start to break down the equation, right? We'll break down if we're going to approach it looking at the forces, or if we're going to approach it looking at different MAs, whatever's given to us, it depends. Sometimes they give us acceleration. Okay, so the sum of the forces equal ma. The force is a physical quantity. This is the unit of the force. It is the Newton. And the Newton is a SI unit of kilogram meters per second squared, right? Mass times acceleration. So the unit of acceleration times the unit of mass. So it's a kilogram meter second squared. In the US, the pound is equivalent to a slug foot second squared. So they say. The approximation of that is 1 Newton to a quarter pound. Do you need to know this? No. Do you need to know the Newton? Yes, 100%. But if you're given future engineers, if you take classes with Dr. Navarro in statics or in any future statics class, many times you'll get forces in pounds. They're not concerned with the slug foot squared. You just continue with the same math, but the unit is just a pound. That is all. Oh, and we have a comment. It means that the force has direct relation to mass and acceleration, so any changes to each of them will have the same changes directly to the others. That's correct, Bafar. Yes. Okay, so now we can look back at our problem again. And using Newton's second law, we can say that what we're doing by slowing down this egg is slowing down the acceleration so that we decrease the force. Now you can see that they're proportional to each other. If you slow down the acceleration, you decrease the force and to a point where the egg doesn't break due to that force. If you do not do that, and the egg just impacts your hand the way it would at its normal acceleration, then you're going to have a large enough force to break the egg. So what we're doing is trying to minimize that force.
So since like you can't control what speed the egg was coming at you, you can only control the time at which it's coming at you.
So yes, but what you're doing is slowing it down, right? So you're slowing it.
Yeah, but you're going from like whatever speed it is to 0. That doesn't change. So if you change the time, you're changing the time that it does that.
You're changing how much position it moves over time. Yes.
Oh, okay.
Yeah.
Position moves over time.
Yes. Yes. What's the Marvel character? Doctor Strange, right? One of those. He can change time. Okay. Nathan says, when the egg goes into your hand, is that a new inertial frame for the egg? No, I don't think so. No, I don't think so. I think the acceleration is just slowing down. It's not a new frame of reference, a new inertial frame, but maybe for the yolk inside, because the yolk inside is still moving. But no, not for the egg. What has just happened is that the acceleration has physically slowed down. Yeah. Okay, guys, I'm gonna start a problem, but I'm just having way too much tea, and I really have to use the bathroom. That's why I'm squirming around. So just give me 2 minutes. If you need to take a bathroom break, take one right now. 2-minute bathroom break. I'll be right back. I'm back. I'm back. I'm coming back. I have returned. um, um, okay. Okay. Just checking if people are out there too with me. I see Bafar in the chat. Okay, I see Mehmet's here too. Thank you. Okay, I see Saja and I see some thumbs up. So, um, and Daniela, hello. Oh, okay, Kian, we're back too. Okay, and Gary, hello. I see the thumbs up too. Okay, great. I see more thumbs up. Hi, Sanjita. Oh, and Andrea, great. Okay, just making sure that we're all back. Man, this would happen in class too. FYI, in at Trade Tech, I would run out of the room and run back in because this happened. I'm gonna leave the pandemic with an even weaker bladder. Okay, I have lots of questions happening here. Let's see. If we throw out a very fast egg when coming back, will it be the same acceleration? Isn't that free fall? If you if we throw out a very fast egg when coming back, will it be the same acceleration? Isn't that free fall? Um, so it's free falling in the y. It's definitely free falling in the y, but in the x, the idea is that we threw it, right? We threw it with some sort of acceleration there. So it will eventually, we are going to physically slow down that acceleration. And then Owen is correct. I think if you throw the egg fast enough, it will cook. We got to test this one out. And then a comment to me, I think we have the same desk chair.
So you're saying that like when I throw the egg, it has velocity, it has acceleration or velocity?
Well,
Like it has acceleration before it leaves my hand, but then after it leaves my hand, it has no acceleration in the horizontal direction.
if this were a simple model of a problem, then it would not have acceleration in the x. But because we're throwing it with some acceleration in the x, and this is a real life problem, there is acceleration in the x here. But it's probably minimal, something that we can neglect in most problems. Um, okay, and then another one. If you slap an egg fast enough, it can cook also. Okay. Before, will it be the same acceleration when it's thrown back? Um, the acceleration, to me, when something is thrown, I think the acceleration is changing because it's going to reach its max point at some position, and then it's going to lose that acceleration. Yeah, it'll be from friction, and that friction actually exists in the air. So that's correct. Yeah, but guys, again, these are details that we're going to get to a point where we can handle these details, but we want to stay within the bigger model of things. Because we're getting a full picture right now of all the physics that's happening. Okay, I thought I left the slide on the problem, but my bad, I didn't. Let's try a problem. Okay, here's our famous hockey puck again. Let me just rearrange things here. Okay, a hockey puck has a mass of 0.3 kilograms. Oh, a hockey puck having a mass of 0.3 kilograms slides on the frictionless horizontal surface of an ice rink. Two hockey sticks strike the puck simultaneously, exerting the forces on the puck shown in the figure. The force F1 has a magnitude of 5 newtons and is directed at theta 20 equals 20 below the x-axis. The force F2 has a magnitude of 8 newtons and its direction is, let's say phi, is equal to 6 degrees above the x-axis. Determine both the magnitude and the direction of the puck's acceleration. Okay. So let us just make sure we know what's going on in the image. In the image, we see the puck and we see forces on a two-dimensional plane, right? The XY plane. One of the forces, again represented as a vector, F sub 1 is 20 degrees below the x-axis, and then the other one, F2, is 60 degrees above the x-axis, and they give us the direction of each one of these. So force 2, this one is 8 newtons, and force 1 is hit with 5 newtons. They want to know then what is the magnitude and direction of the acceleration. And then I think, I hope I hope we remember that no matter what.
Professor.
Yeah.
I'm sorry. It's force. F force 1 is on the bottom with 5 newtons, and the force 2 with the 8 newtons is on top.
Thank you. I swear to you, I do this every semester. And I remember like 2 semesters ago that I switched it when I was solving for it, and it confused everyone, but no one told me. So we just solved it with the reverse numbers. Thank you, Kian, for catching that. Okay, so what is the total acceleration, right? Now, this doesn't change. Magnitude and direction, we know acceleration is equal to ax plus ay, and we know that the magnitude here, we know that the magnitude will be the square root of the sum of the squares, and the direction will be the tangent of the y component or the opposite over the adjacent. Nothing has changed. We just have to figure out what are these accelerations. So let's bring this over to the next slide and keep our image. And here goes, for the first time ever, we always start with Newton's second law. And so Newton's second law is F equals ma. And we are clearly in 2 dimensions here. So you want to start with all in the X or all in the Y. And then you want to think about how you want to solve this problem. The first thing I'll say is your line of attack is either solving for the forces, adding up all the forces, or solving for mass and acceleration, because sometimes you'll be given accelerations instead. In this one, clearly they give us the forces. So we are going to solve in terms of forces. And I'll show you what that looks like. So here's the sum of the forces in the x direction, right? So the sum of the forces in the x direction, we know that this vector 1 will have an x component and vector 2 will have an x component. So the force in the x component of 1 and the x component of 2, and we know how to break this down. We know how to resolve that into its components using sine and cosine. F1 cosine theta, and then here we have F2 cosine theta. So this is F2 cosine theta, and then F1 cosine theta would go the full way there. And so we can add that up. Now I'll ask you guys, we know that this puck is going to be moving, so this whole thing will equal max. Okay, so when you write Newton's second law, this is what you would have written. The sum of forces equals max, but you then have to actually sum up every single one of the forces. Let's do it again for the y now. So the sum of the forces in the y are the 2 y components of the forces, and we can break down those y components in terms of sine theta. Okay, and this will equal may. And we know that the objects are moving, so this A is dynamic. It will have a number. It is not equal to 0. Okay, and this is the thing that we're looking for, right? AX and AY. I'm just clearing my throat. That's it. Okay, so let's solve for the accelerations X and Y, which is what we need in this problem. So we isolate the A sub X, all of the sum of the forces on top over M. We do the same for AY. And the sum of the forces in the X is the full line that we just solved for, the X component of force 1 and the X component of force 2 over the mass. And for AY, we see the same. Okay, now we know these values. We know F1, we know F2, we know theta, and we know phi. So we can plug these in. And you can get the actual values of AX and AY. Okay, this is all nice so far. So we have these 2 values, and now, again, we pull in everything we know from our vector math. The total acceleration is then the square root of the sum of the squares, right? This is ax squared, and this is ay squared. And so the acceleration is 34 meters per second squared, and now we get the direction. In our direction here, we're just going to use a different degree because we've already used theta, we've already used phi, so we're going to use beta. So the angle beta is the same, the tangent, inverse tangent of the opposite over adjacent. So you see 17 over 29 and 31 degrees. So this is all really nice. And
So where's the 31 degrees at? Like, could you draw it on the picture?
yeah, actually, you can draw it too, right? This is 60. Anyone can draw this. 31 degrees is right there.
So that's the direction that the hockey puck will actually go in.
Yeah, and then the length of this vector, which would be the magnitude, is 34. So it's probably way, way longer if it were on the same scale of these arrows. Yeah, so guys, remember this math here, it's not going to change. So 31 degrees is 31 degrees that you knew semesters ago too. Yeah. So up until this point, and the physics really stopped here. It stopped here. After we've established Newton's second law, the rest just becomes plugging and chugging for the thing that you're solving for. So all of this is now math. And let me say, from grading most of the exams, not all of them, that showing your work is a benefit to you. Because if a calculator error happens, but you wrote all this out and you end up with some funky number here, but you wrote everything out the correct way, then I know you did it right and your fingers messed up or the way you wrote the number messed up. And a question from Daniela, what is that symbol next to F2 cosine theta? Oh, I think it's phi. Yeah. Thank you. Let's write it out. Phi. Some say phi. I think it's phi.
It is.
It is, right? Yeah. So this is a very complete problem and very, very nice to see. The other thing I'll say about when you're working these problems out, I really appreciate everyone's efficiency in setting up a problem and working it out. Don't be afraid to use up more space on the paper. It's okay. This is for everyone. It's okay to use all the space on the paper, but it's also okay to fill up all the space in a line. So just as long as you are able to write out everything, that's what matters. Okay, so this was a great problem, and we've now worked with some Newton's second law and the applied force. There are several forces that we can sum up within the forces, that like the sum of the forces in Newton's second law. There are a ton of forces, and our goal is to try to get to 4 or 5 of them by tomorrow. Here is our second force, the one that you guys know, gravitational force. So the gravitational force is the same as saying our weight, right? So now whenever we say the force due to gravity, we will say F sub G. Do not confuse this with the actual value of G. Let me remind you, oh, that does not look good. Let us remind ourselves that this G is an acceleration, right?
A negative 9.8.
Yes. So the force due to gravity is equal to, just like Newton's second law tells us, mass times acceleration, where that acceleration is now due to gravity. So sometimes you'll see me write it like this, just, so that we know that it's Newton's second law, but this is absolutely the same thing as saying mass times gravity. So F sub G. Okay, so the gravitational force tells us that all objects fall down to Earth. But what it's really saying is not the direction down, but the direction towards Earth, attracted to Earth. And so an attractive force that's exerted by Earth on the object is present because of the mass of Earth. We don't know what the reason behind that is. That's very much a philosophy question, but we know that the mass of Earth will create a gravitational pull. And so this is what we call the attractive force exerted by Earth onto the object. This is always going to be directed toward the center of Earth, which in our frames will always be in the direction down. The magnitude of this is also called the weight of the object. So sometimes you will see, instead of writing F sub G, which is the force due to gravity, you could also write weight, W, and the two are equivalent to each other. So the sum of the forces equals ma, where the acceleration if the force is due to gravity, if the acceleration is due to gravity, then the sum of the forces here would be the force due to gravity. And notice that we subscript it that way. And so F sub g will equal m times g. And this is the same as, say, Newton's second law, F equals ma. So all of the forces equal ma, and then the sum of the forces also equals ma. So there's different ways to solve for this.
So if
And
the only force acting on it was gravity, then it would be that.
that's right. That's right. If the only force acting on something is gravity, for example, if I write the sum of the forces, this is how I like to write it in class. The sum of the forces equals ma. And now you actually have to add in what are all the forces, right? And if so, if the only thing acting on it is the force of gravity, then we would just put Fg. But if someone is being I don't know, weighed down with something else, we could write an applied force. Or if someone's being acted against the gravity, like I don't know, some kind of like wind tunnel or something, you could also add in the applied force.
So like me sitting on my chair, is the gravity is acting on me, but a normal force is acting on me in the equal amount?
Yeah, yeah, that's exactly right. And so in that case, this sum of the forces would equal 0. You would be a static situation. Okay, so the magnitude of this force of gravity is what we call the weight of the object. So you could also write W, right? And again, this gravitational force is very much due to the mass of the Earth. This is a gravitational force. So they gravitate towards each other based on the mass. Oh, I see some questions. Can you please go back to the last slide? I hope it's this one. Yeah, I hope it's that one. Okay, another question. Can you explain what is the difference between the two equations? Which two equations? Probably these two. One here is the magnitude. Okay, I'll go back to the last slide in a second. Oh, you're going to screenshot. Oh, God. Okay, 1 second. Okay, screenshot quickly. The difference between the two equations, one was vector notation for the force of gravity, all in terms of gravity. And the second equation was in terms of the magnitude only. So the weight of this object is the magnitude. That's the only difference between those two. I hope that is what you were talking about. If not, let me know. Just type it out. Okay, so again, the word gravity means that something is gravitating towards us, and it's only due to the mass that is exhibited by that object. So, so this force of gravity will depend on how close you are to the mass itself. So the value g will vary with the geographic location. So if we have our equation here and g is equal to 9.8, then gravity will decrease. That value of 9.8 will decrease the further away we are from the center of Earth. So objects weigh less at higher altitudes than at sea level, right? And here's your quick example. If a student has a mass of 70 kilograms and the weight then where g is equal to 9.8 would equal 686 newtons. But if they were at the top of a mountain, very, very high mountain, and gravity were 9.77 meters per second squared, so just a little bit smaller, the weight of the student or the force due to gravity would be less. And so the person would weigh less at a higher gravity because they're not being pulled down to Earth.
Do we, like, for our purposes, neglect that?
Yes, unless the problem tells you, yes.
Okay.
There will be once in a while, where the problem will tell you, assume the gravity is this value. Yeah. Okay, so there's a clear difference here between mass and weight. And remember, this was what we talked about on day 1 when we talked about why weight was an approximation of mass. And you see this too on the moon, of course. The moon is a much smaller size than Earth, so it has a less mass. Less mass equates to a lower gravity. And so you see that this gravity is like I don't know, maybe like a sixth or a fifth smaller, 6 times smaller than the one on Earth. And so even when astronauts were training to walk on the moon, depending what your beliefs are there. I do believe it. When the astronauts were training to walk on the moon, the mass was felt much smaller of the pack, right? So even though the actual mass of their pack on Earth would be something like 300 pounds, they trained with packs that were something like 50 pounds so that it would simulate what or mimic what they would feel on the moon because the gravity is much less, right? You're not feeling a gravitational pull as strong as what you feel on Earth. Um, yeah, so now we have two forces to talk about. We have an applied force when something is pulled, pushed, and we have a gravitational force too. Let me see. Okay, we have like about 10 minutes before we maybe talk about a break. So we can now come to ta-da-da, our last law, Newton's third law, that I think you guys have also probably heard about. If two objects interact, the force exerted by object one onto object two is equal in magnitude and opposite in direction to the force exerted by object two onto one. So here it is that they are equal in magnitude and opposite in direction. Equal in magnitude and opposite in direction. Notice the notation changes. This notation tells us which one is exerting the force. The first notation, the first one is exerting the force. So this is object one exerting onto object two. And I'll clarify that on the next slide again. Let's go to the next slide. So this is the equal and opposite. Okay, so this notation, F sub AB means the force exerted by A onto B. So F sub 1, 2 means 1 exerts onto 2. The reason this is important is because of directions. You want to see which is the mass, which is the one that is going to pull something or have something gravitate towards it. And we can call this an action force. And there's object one. So in this case, object one is going to exert a force onto object two, right? And that force that it's going to exert on it, object one is going to pull or gravitate object two towards it, right? So force of one exerted onto two. We can also have then the opposite, where the force of two onto one is the reaction force. The force of object two exerting or pulling object one onto it. So notice how the arrows are pointed in a different way. Here's the summation of that. Okay, the force of one onto two is equal and opposite to the force of two onto one. So object one here is exerting this force onto object two. It is pulling object two towards it. Object two here is exerting this force onto object one. Object two is pulling object one towards it. Even though one has a larger mass than the other, they are still pulling with some force. And they have to be equal and opposite. So when we see this, right, we know MA and A, these equations have to somehow balance each other out, right? Okay, and so, oh no. Okay, these forces that are equal and opposite for when the objects are acting each other must be of the same class of forces. So in Physics 101, we're only going to really look at gravitational forces. In 102, you'll look at electrical and magnetic forces too. So it shouldn't be too much of an issue. Now, the big one I like to clarify here, because you might say, well, let's say an object is falling, an apple falling to the earth. That means the earth is pulling on the apple. Does that also mean that the apple is pulling back on the earth? A according to Newton's second law, yes. And Nathan says yes also too. Yeah. Yeah. It is pulling on it, and it's actually pulling on it in an equal magnitude. But let us look at what this would look like, right? The mass of the apple and the acceleration of the apple here, or the force of the apple onto the earth, is equal to the force of the earth onto the oh hell onto the apple. Ignore that little c. That was a So what you're doing here is balancing out these equations. Now, think about mathematically what this looks like. Um, okay, when an object falls down to the earth, the apple has a very, very low mass. Compared to what we see the earth moving, do we see the apple? Does the apple look like it's accelerating faster than the earth? Does it seem that way? Does the earth feel
Yeah.
like it's accelerating back at you?
Yeah.
Yeah, the earth is never going to feel like it's moving back at you. It's actually coming at you at a very, very low rate. But the apple is accelerating really quickly, the earth, very so quickly so that we can see it, right? And so the mass of the earth here is going to be really big, and the acceleration of it is going to be really low. And these two will balance each other out. Mathematically, this has to be physically true. It has to be physically true. So,
So
uh-huh.
does this mean that, like, as the human population increases, that our gravitational force increases because we make up the mass of Earth if we're on Earth?
um, the mass, the gravitational, okay, so those are, there's many sub problems in there. Um, we don't, I would say that people to people, we gravitate one to one. As a whole, if we were, okay, if you were to look at the whole mass of the earth, sure, you could do that, but I don't think it's significant enough to change the mass of the earth, our human population. Now,
But I mean, like, the mass of one person compared to 1 billion people is like a number that it might not be significant in terms of the Earth, but it's significant in terms, like, you can quantify it.
you can quantify it relative to people, but relative to Earth, I'm not sure it'll make a big difference. I actually don't really know.
Yeah,
So
Nathan just brought up a good point. He said all the mass to make people comes from the earth.
From the
We
earth,
don't
yeah.
get any, so the mass should be about constant, really, other than what we eat from meteorites that fall from outer space or whatever.
yeah,
Like
so,
they say that you can't create or destroy, matter.
and we'll do that next week. So it's not significant when we're talking about the Earth's mass, but if you were to look at like sub things, like for example, would one person gravitate towards 10 people? It might not seem that way, but yes, eventually does. If you have a table of pool balls, right? A pool table with balls on it, and they are not in motion, and they look like they're not in motion, they are actually gravitating towards each other. We just can't measure it or sensor it with sense it with our eyes, but physically they are moving towards each other. It's pretty cool. Um, yeah, that is pretty wild. Okay.
Like metaphysics meets physics.
Yeah. It it's sometimes it's unbelievable, but I have to believe it. I do believe it. Okay, so let us look again at Newton's third law and just bring in another force that now makes sense to us. We've already said it so much in class. Let me give us 5 more minutes before we talk about a break. Okay, so let us analyze this problem of the computer monitor at rest on a table, right? So when we look at the computer monitor that's sitting at rest on top of this table, we can first start out by looking at what is the force acting on the monitor. And of course, we'll say that the force of gravity is acting on the monitor, right? The second thing we can say is that the monitor is static. It is not moving. And because the monitor is not moving, we know that the table is holding it up. Right? The table is something that's holding it up. Yeah, and Keo makes a good point. It's not it's not intuitive, but wait till we get to torque. Man, wait till we get to torque. You're gonna love it. Um, it'll make things make more sense, I hope. Um, Okay, so we're looking at this monitor on the table. We know the force of gravity is acting on it. We know the table is static. It is the monitor is static. The monitor is not moving in any direction. We know it's not falling down to the earth because it's being held up by the table. So because it's being held up by the table, we can now look at what is the force that's acting on the monitor by the table. What is the table doing? Whenever an object is in contact with a surface, we are going to call this a normal force. This is a normal force. You can also write it this way with a unit hat thingy. Actually, I think I read it that way more often. Um, this is a normal force, and notice that this is the force of the table exerting a force onto the monitor. And this force is only present because it is in contact with that surface. Anytime two objects are in contact with each other, there will be what we call a normal force. If you are sitting on a chair right now, the chair is applying a normal force but back up at you. Your table is sitting on a floor. The floor has a normal force acting on it.
Is like the moon, is the Earth acting as a normal force on the moon, keeping it in its orbit?
No, that's a gravitational force.
No.
But it is, yeah, what's keeping it in orbit is a force, and it's the gravitational force due to mass. Remember the definition here. For a normal force, it will always be due to contact. Yes. Anytime there is contact between any two surfaces, there is a normal force acting there.
So like a magnet are acting on a piece of metal, if there's a normal force there? Because like the magnet's drawing it in, but the object can't go through the magnet, so it's acting, the magnet's acting back on the metal.
There is a contact force there because they are touching each other, but what's more significant there is the magnetic force. But yes, they are contacting each other. Anything that's contacting is there, but we'll realize later that a magnetic force does not need physical contact too. So whenever you talk about magnets, we don't usually associate them with normal forces unless what you said is that they're touching.
Okay, so like what's like a better example of like a horizontal normal force? I'm just trying to find like.
That's a great way. Here's my hand, here is my phone. I am pressing onto this here, right? So the normal force that's acting on the phone, and of course-
Is your hand?
That's right.
Or is it your finger, and your finger is the other force?
Yeah, that's right. That brings us to our next point, which I don't think I put it on here, but I don't think I wrote it on here, but I'm just gonna write it. The normal force is always going to be perpendicular to the surface. So if I'm holding up this box of tissues, we would actually be, doing
lies. I said lies. There's no tissues there.
Here, I'm holding up this box of tissues here, right? Or let's just pretend it's floating. And I'm using my finger here and I'm pushing against it. There is a normal force acting perpendicularly out from this box onto my finger, and my finger is applying a force. But there's a normal force acting perpendicularly outwards. And
Is that normal force your hand, or is it the tissue box?
The normal force was the tissue box perpendicularly out. My hand was an applied force.
So like the hand you have behind it was the origination of the tissue box's force?
The contact. So there's anywhere there's contact. If there's contact in two places, then there's a normal force in two places.
Okay.
So notice the normal force here. There is contact here, and the normal force is drawn perpendicularly out. There's a normal force here from the ground to the table, and it's drawn perpendicularly out from the ground. I have some questions really quick before I move on. I'm kind of confused about the notation. What does FFP refer to exactly? I'm going to temporarily mute you, Randy, just because we can hear your background, but unmute anytime.
Oh, sorry.
It's okay. Anytime you need, just unmute. Okay, so let us look at this notation here. Before we knew what a normal force was, we knew that the table was exerting a force onto the monitor. So that's what the T is. The table is exerting a force onto the monitor. But this force falls into a class of forces that is due to contact. When they are contacting each other, it's not necessarily an applied force like something pushing or pulling back on it, but it's getting it's it's holding it up. The monitor is being held up by the table solely due to contact. So this force here is a normal force, but the normal force is from the table to the monitor. So that's what the notation is, the table to the monitor. That's actually the next line. Let me continue then. Oh, and then another question.
So table exerting force onto monitor.
Yeah. And then Owen says, is that why your finger gets bent back when you push on the box because it's getting pushed back? Yeah, there's an equal and opposite force there. Okay, so the force of the table onto the monitor is a normal force that is due to contact. So this is a normal force that's due to contact. So if we know that many other forces are at play here. For example, we know that the monitor is this the monitor? The force of the monitor exerted onto Earth. Yeah, the monitor is pulling back at Earth. Although we know all of these exist, the only ones that we are going to look at are the ones that are initiated and centered around the monitor. So we look at the monitor only and only look at the forces there. The reason we're doing this is because the initial question was analyzing the situation of the computer monitor at rest on the table. So we pull out the computer monitor and you see that the only forces that are acting on the monitor is the normal force from the table and the force of gravity that acts on the monitor itself. Now, using this, we could now isolate the situation and look at the Newton's second law, the sum of the forces. So the sum of the forces here is equal to 0 because the system is static. So the first, I would actually write it like this because it reminds me that I need to actually sum up the forces, equals ma, and the acceleration of the monitor is 0. So this is where everything comes from, right? So now we need to fill in this gap, this here. What are all the forces acting on it? We look to our figure, we see that there are only two forces acting on it, and we're writing them in vector notation. So the vector notation is, first we add up all the forces, the normal force and the gravitational force. So we could write here FTM, and we could write plus FG. Now, in actual notation, we could then write that this is the normal force, N, which is what you should write, the normal force. And F of G, we know, is mass times gravity. And this whole thing is equal to 0. Now we could write this is all in vector notation, and now we could write it in unit vector notation with the magnitude so that we can include directions to everything. So if we look at this normal vector, the magnitude is the letter N because we don't actually know what the magnitude is. So we put a variable, a constant there, N, and we know that it is directed upward. So that unit notation is J hat. Now we look here, right? The mass comes down and we know that gravity will be negative and the vector is pointed downwards. So negative G, J hat. And this whole thing then is equal to 0. So now if we look at the magnitude of everything, because everything is in J hat, right? We can just look at the magnitude of things, and we bring this over to the other side. And here you can see what we suspected was that the normal force is equal to the gravitational force, that they balance each other out. Now, is the normal force always equal to just the gravitational force? Not always, because sometimes, and here's a good example of this. Let's say, you have your book, some book, and at the very moment here, it's completely balanced. Let's say my hand was the table. Pretend my hand's the table, right? The notebook is on the table. At this moment, we have a similar situation to what we see on the screen. The normal force equals the force of gravity. What if now I come with my my hand and I push down on it, I'm adding an applied force in addition to the gravitational force. Now, these two forces together will have to balance out the normal force. So, there are scenarios where the normal force does not always equal the gravitational force, especially if we pile on things or if you're leaning on a table but the table doesn't break, right? You're adding more forces there. Um, okay. Um, can we go for 5 or 10 more minutes? How is our energy out there? Or do we really, if we need a break, we can take a break. But how we do it?
Uh,
Through the roof. Okay. I see a thumbs up. Randy, what do
so
you think?
I'm good either way. I just have a question.
Okay. Okay. Let's keep going and I'll see if we get to a stopping point. Let's hear your question.
The what you mentioned with the normal force not equaling gravitational force, like, so I have a table here. The table has a normal force acting up on it, but then there's also all the things I have on the table. Does the table and the things, does the all the stuff on the table, they all have normal forces acting up on them? So isn't the net force still zero?
Yes, the net force is still zero.
But then
But
the normal force
but
is
the
not equal to gravity. Can you explain that
right.
a little bit more?
Yeah, so in this situation, we only have a monitor, which is represented by this normal force here, and nothing is acting on it, just the force of gravity. But what if instead we had several things on it, right? What if then we say the sum of the forces equals the normal force acting on the monitor, the table to the monitor, the gravitational force. But then let's say someone walks by and just start pushing down onto the monitor. There would be a push, an applied force. But the monitor still doesn't fall through. It's still just sitting there, right? So it's equal to
So
zero.
there's more than just gravity acting downward, and then the normal force then increases though, right? Because the
Yes,
table's not going down.
yes, that's exactly right.
Oh,
So
I see. So what you're saying is like it's increasing the force of gravity. However, the normal force still matches, but it's more because you've increased gravity even.
we don't increase gravity, we're increasing other forces, but this does
Yeah.
increase the value of the normal force.
So like gravity is separate, but it's like in the same direction as gravity.
Yes, yes. Gravity plus an applied force that's pointed down, right? Something that's pushing down on it. Yeah. So the normal force doesn't always equal gravity. That's just what I want you to be aware of. Not always. It does in most situations, but not always. Okay, so what we did here was simplify this problem very nicely from looking at different forces acting on the monitor to just the problem that we wanted, which was the monitor and the forces on the monitor that have to do with the monitor being static on the table. And so that is our goal from here on out in chapter 5 and the rest of physics, is to look at a situation and simplify it. And we're going to do this using free body diagrams or the FBDs. If you're an engineer, you will carry these free body diagrams through your future courses. So let's get comfortable with it. So when we first looked at the computer monitor on the table, there were many forces in the situation, right? The table acting on the monitor's force of gravity, but we know that's equal and opposite. So the monitor is also pulling up at Earth, right? If the table is acting on the monitor, we know that the monitor is also acting on the table, equal and opposite. So a lot of forces are acting here, but we were only concerned with what was happening in the monitor's motion. And so, from many forces in the situation, we want to dwindle it down to the two and what is acting on the object. So, we look at only the forces that are acting on one object and the forces on that diagram. And then we're going to take it one step further and simplify it to a drawing that looks like this. And this free body diagram, then, we will draw the object as a dot and we will apply the forces with the same directions and length onto that dot. This will isolate only the forces that we need on the object. So the monitor becomes the dot. Sometimes you'll see a square, depending what book you use. And this vector force here is then drawn down here. And then this one here pointed up, the normal force is then drawn at the top. And now when we do Newton's second law, it becomes really obvious to us when I say sum up the forces in the y direction. You look at your free body diagram, and you will look at only things that are acting in the y direction. If you have in the future, near future, you might have a force acting this way. Then you would have to break down that force into its components and find its y component, and you would only add up that y component here. Only anything in the y will add up. So the normal plus fg plus whatever that y component is, which is usually the force times sine theta, right? Or whatever direction it is. So this free body diagram will help us see that. And this is what your lab will be later today. So yeah. Okay, let's see if we can, we got a grip on this. We're doing okay on time. Maybe at 12, I'll check if you guys need a break, because we're not robots either, you know? Okay, let's try this question. If a fly collides with the windshield of a fast moving bus, which experiences an impact force with a larger magnitude? The fly, the bus, or the same force? Okay, I see a whole bunch of answers.
The same force?
Okay, and I hear from Randy too, and Owen and Amir and Saja and Henry and Noah and Bafar also all saying, and Mehmet also all saying C, they will be the same force. And Amir tells us that it is because of Newton's third law. So no matter what is the mass of the object or the acceleration of the object, the two combined, the force, must be the same for each, equal and opposite. Let us analyze it a little bit further. Same situation, the fly collides with the windshield of a fast moving bus, which experiences a greater acceleration. Let me remind you that the force of the fly onto the bus must equal the force of the bus onto the fly. Okay, I see two responses from Henry and Annette that say A. Anyone else? Okay. I hear and see a yes, you concur too, Keon and Alexandra. Great. Okay, so now that I have at least three responses, we'll see, yeah, the answer is in fact the fly. And Sanjita, thank you. The answer is in fact the fly, because when we look at the mass of the fly and the acceleration of the fly versus the mass of the bus and the acceleration of the bus, you'll see that the mass of the fly is really low. So the acceleration must be really high to match the high mass of the bus and the low acceleration of the bus. And this simple arrow relationship, a la Klee, is a good way to just justify and convince yourself. Yes, Nathan tells us because it's less mass, it must have a higher acceleration, right? Yeah, because the fly has such a small mass. Yeah, gruesome. Okay. The fly has a small mass.
That fly is still standing there. He's so happy to be going faster.
The fly is zooming.
Yeah.
The fly is zooming, right? And the large mass of the bus will, of course, exhibit a small acceleration. Okay. Oh, and then Henry has a question. So on a tiny scale, the bus decelerates when it hits the fly. The bus decelerates, it slows down when it hits.
Because if they're happening in the opposite directions, then yeah, right?
Yeah. And I like that you say tiny scale, but what you mean tiny scale, it means a very, very small interval of time where we can now see what is happening in a like a micro scale, microseconds it's probably happening. And then yes, poor fly splat.
No, he's just moving in the other direction now. He caught a ride.
Yes, Randy, that's right.
His exoskeleton is serving him.
Or Owen says he's moving in many directions. Yeah. Maybe we should change the problem to a strong June bug. I agree. They have a strong shell. Okay, let's try this one. Let's continue with this conversation. A large man and a small boy stand facing each other on frictionless ice. They put their hands together and push against each other so that they move apart. Who moves away with the higher speed? Okay, the man with quickly says boy.
They move away with equal speed.
That's an option. Who moves away with the higher speed? So if they move away with the same speed, that would imply the same mass.
Oh, okay. So that's wrong.
It's okay.
Went with the road less traveled. It's like when there's a small person or a big person and you're doing this, it feels like you both go away pretty fast.
Yeah, especially when it's frictionless, right?
Yeah.
You're gonna both move, and that's fine. That's totally fine to think that. But we have to prove it mathematically, and then mathematically we'll see that the relationship is based on the mass. So yeah, I see several people say, "Boy, the." Oh, Owen also says the same, and then he says, "Never mind." So
will the man get further since he has more inertia because he's bigger?
so so let's relate that back to the speed. If the boy, okay, so the answer is the boy. The boy is moving faster because he is a smaller mass. Now, what does the moving faster tell us about distance and displacement?
Oh, he has more inertia or more distance
Or distance.
over a faster time.
Yeah.
But will he slow down sooner than the man will? Like the man might go slow and get further, but the boy could go fast and get less far.
Who has less resistance to motion?
The man.
The man has higher resistance to motion.
But like, doesn't he have less resistance to slowing down once he's got started?
Okay, those are two different statements. Let me think about what you just said. Who the man has higher resistance to motion because he has a higher mass to change. So you need more of a force to slow down the man.
Yeah, exactly. So like this, I guess there's no friction though, so neither one will ever slow down.
Yeah, those yes. I just have to think of the way we eat. Okay, let's try this question. Who moves? Oh, we did this. Who moves farther while their hands are in contact? And yes, we see Bafar and Luis say the boy. And the boy is true because he's moving faster. And we know, velocity faster means a larger, right? A larger speed over time. So yes, the boy is also moving faster. Okay, so we're on great pace. I really will check in on you guys at 12 o'clock and see if we need a stretch or something. So far we've done, check us out. We've done applied force. We've done gravitational force, and we've done the normal force. We've done the normal force. Here we go. Are we ready for a very, very common force? The next one coming up. Okay, now the next force that comes up is a situation whenever there's anything connecting two things that are like maybe a rope or a string, a chain, rope, string, chain, a shoelace. I don't know. Anything that acts like a rope. Yes, Sanja, tension, that's right. So let us make some quick assumptions before we bring in tension, but this is all about tension. So if ever we say an object is in equilibrium, we are going to be interested in what are the external forces that act on the object. For now, and only for now, we're going to neglect friction. Whenever there's a surface, there's a question and it tells you the surface is frictionless or just neglected, you can just ignore it. If it doesn't say it and you see, let's say, a triangle and something sliding down the triangle and the line is smooth, that means it's frictionless. If you see a triangle with like a very rigid line or very like, that is a rough surface that will give you a friction. So for now, we want to go with frictionless surfaces. Whenever something is light or negligible, the mass is negligible, then you can just ignore the mass. And this will let us focus in on other forces that are at play, for example, the tension. So whenever a rope is attached, anything that acts like a rope, the rope is going to exert a force on the object that is directed away from the object, but parallel to the rope. This is going to be the tension. I'm going to draw this out for you in just a second. The magnitude of that force will be T, and it will be the tension in that rope. That is the scalar quantity. The force vector for tension is drawn like that, with a T and a capital T. If you want to put F sub T, it's fine too, but normally we use tension. So the way that we're working with free body diagrams, so we need to be able to draw these forces. And so the direction will always be away from whatever the object is and parallel to the rope. So let us say we have this rope, and this rope, any ideas which boat originates the rope? Where does the rope originate? This one maybe? This is the right boat?
I would think so. Yeah.
Okay, we all agree. The rope is going to originate here, and the rope is going to pull onto this object. This is the object. This is the object, the other boat, and the rope starts here. Let's just say it starts here somewhere, right? And here's your rope. So the direction of the tension is going to be away from the object and parallel to the rope. Away from the object and parallel to the rope. You guys saw how I drew that? Now think about what you would see. This rope is pulling on this object, and so the tension is felt away from the object, and it's felt along the direction of the rope. How would
Isn't it also
that?
felt in the other direction?
Well, depends on the point of. It all depends on the point of view of where you're pulling. Because think about the word tension. You have slack in a rope, there is no tension. Yeah, you have to pull on it, right? So like the scenario with my two hands is complicated because there's two objects here. But let's say I'm pulling, the rope starts in one place and I'm pulling against it. The object that's going to feel the pull is where the tension is going to leave from that direction. So the rope starts on the boat on the right. We take the rope and hook it onto this boat and pull this boat. So
it's a matter of perspective then.
Absolutely, it really is, of what it is you're looking at, and you'll see that in a second too. Okay, let's try this tension force on the next slide. So here you have like a a lamp, or I don't know, like a lamp or a chandelier of some sort. I don't know what these words are. A lamp, let's say a lamp. And in our drawings, we would draw out a lamp, right? And now you can draw what are the forces acting on it. First, we can say the lamp is in a static position. It is not moving in any direction. We know that the force of gravity is acting on it always. That is true. Now we also know that there's this rope here, and this rope is pulling it upwards. So the object is here, and the tension goes away from the object parallel to the rope. So we take this one step further, and we're going to try to draw out our free body diagram for this too. So the net force on the object would be equal to 0. And so the free body diagram would look like this. You have your dot with tension upwards here and the force of gravity down. And this is the free body diagram. Now I'm trying to, these arrows should be to scale, like they should be equal because they're static. The chandelier is static and nothing else is acting on it. So I can start with saying Newton's second law, the sum of the forces here. The sum of the forces are equal to ma, and there's no acceleration here. There's no acceleration, so it's equal to 0. And so now we actually have to sum up those forces, right? Sum up all the forces that are there. In magnitude notation, we can just add the arrows that we see on the free body diagram. So the sum of the forces in the y direction are equal to the magnitude of the tension acting upwards and the force due to gravity acting down. In a magnitude notation, that down is a minus. So tension minus the force of gravity. Notice that there's no vector notation here. This is all in magnitude. We're summing up the forces in Y. And all you're doing is looking at your free body diagram and adding up the arrows the way that they are drawn on the free body diagram. And we know it's static, so it's equal to 0. So in this situation, we can bring this FG over to this side, and the tension here is equal to the force of gravity. So even though we don't have a value for the tension, if we know the mass of the chandelier or the lamp, then we can solve for the tension in this situation. Does that seem all right? Okay, let's try one more example. Okay, thanks, Nathan. I see you guys. I see Saja also. Perfect. Okay, let's try one more example with these free body diagrams. Let's see. Okay, let's look at an object that is not in a static position. It is moving, so the acceleration has to be greater than 0. There is some net force acting on this. This crate is being pulled to the right. So we can start with Newton's second law. Sum of the forces equals ma, and we're going to sum up all of the forces. So I would write this as the sum of the forces, all of them, equals ma. So let us look at the free body diagram for this. Now you guys tell me, in the y direction, up and down, this is where it becomes useful to put your I hat and J hat. In the y direction, is there any movement of the crate?
No.
Correct. I see head noddings, I hear no, and I see lots of no's. So the sum of the forces here in the x, we should know, will eventually equal 0. What about the sum of the forces in the x direction? Will they equal 0?
No.
No, they will not. Correct. I see Daniela also in the chat and Saja also. Because we see this arrow tells us that there is an acceleration, and we know this acceleration, that's an equal sign, is going to be in the x direction somehow. Okay, so let us look at the free body diagram here. You guys tell me what forces are acting on this. Anything you might come up with. What's acting on the crate?
Oh, Sasha just said it. Yeah, normal force up.
Okay, so we have from the floor here, right? From the floor here, we're gonna have some normal force acting up. Okay. Thank you, Kian and Saja. Oh, and then Owen and Mehmet say we have also gravity acting down on it. Yeah. What else?
And gravity of Earth acting up towards the crate.
Yeah, and that is in the perspective of the crate pulling on the earth. But we want to know what is acting on the crate, not what the crate is acting on. What is acting on the crate? I know this will sound super confusing, but focus on what is affecting the crate, right? But you are right, that force does exist there. Oh, and then Saja and Henry also say tension. And Daniela says, are we assuming a frictionless surface? Yes, because we see that there's a nice straight line right here. And tension to the right. Now, here's where we want to be clear of how to draw this tension. This person is pulling with this rope, this object. So we go away from the object parallel to the rope. And these are now our 3 arrows, and we can draw our free body diagram now. Our dot with our tension to the right, the force of gravity down, and the normal force acting up on it. And look very nicely, you have your reference, your compass, right? X and Y. Or you can also write I hat and J hat. I actually prefer I hat and J hat, but you can put X and Y. Either one is fine. So let's bring this over to the other side and sum up the forces from Newton's second law. Okay, so now we want to look at what is being added in the x direction. Some of the forces in the x will equal ma. Some of the forces in the x will equal ma. The only thing acting, if you look at your free body diagram, the only thing acting in x is this tension. So all we write is the magnitude of tension. And we can rework this and then solve for the acceleration. And the acceleration is due to the tension over the mass. We can do the same thing for the y. The sum of the forces in the y are equal to 0, and the forces acting in the y, we look at our free body diagram and we sum up only the arrows acting in the y direction. So the normal force acting up and the force of gravity acting down is a negative because it's pointing down. N minus Fg equals 0, and in this case, the normal force equals the force due to gravity. So that's I think, a good example of another free body diagram.
So then is there like so your y is 0? Like your y force is 0? Or yeah.
Your y force is 0, and you can confirm that with the picture that when this box moves, it's only going to move along the horizontal plane and never along the vertical. And so that's why our sum of the forces in the y should equal 0. But we actually have to sum up all the forces, and they will have a net force of 0. Okay, we have about 4 minutes before we take or we talk about a break. We should take a break. And so let me just throw this one at you guys. It's the same forces we've been talking about, but now it's that normal force. It's what we were talking about with the book and the normal forces. The normal force does not always equal the magnitude of the force of gravity, right? Here's a situation. Imagine a book, perhaps your favorite book, lying on the table, and you push down on the book with some force. Here's your favorite book on the table. Because it's on the table, the normal force is acting up on it, and we know the force of gravity is acting down on it. But you also push down on the book with some applied force. Yes, your favorite PDF. I should update this for like 2020, right? 2021. Your favorite tablet, your favorite PDF. Yeah. So now we can continue with what we've been doing, right? Summing up all the forces. We know the book is at rest. The acceleration is equal to 0, so it's a static system. The sum of the forces in the x should equal 0 because there's no horizontal motion. But in the y, we now know sum of the forces equals 0, so let's sum up all those forces. We look at our free body diagram. If we were to draw it, you would see the normal force. You would also see an applied force, and you would also see you would also see a second little vector of the force of gravity. Now, if you didn't know that they're not all going to be equal, you don't have to draw them to scale. It's okay. It's okay. So now we just add them up based on what we see in our free body diagram. The only one in the positive direction here is the normal force, so the n is positive. The force of gravity and the applied force are all pointed down, so minus Fg minus F, and this is all equal to 0. So we move things around, and here's a great situation where we see that the normal force is equal to the gravitational force plus the applied force. So in this case, the normal force is greater than the gravitational force because it also has this additional force added to it. Yeah, and this is a good place for me to emphasize that the normal force is always perpendicular. Let's say you have one of those cool hipster diagonal bookshelves, right? And this is a bookshelf. And you put, again, your favorite book or PDF here, right? And this is physics book. This is a little better drawing. Oh, okay, that's a better drawing. And you have this diagonal shelf. The the shelf here is going to apply a normal force, and the normal force will be perpendicular no matter what, even if it is a diagonal line. Nathan. Nathan with a great question. My little heart. Where does the normal force come from? Atomic bonds. Yeah, it's from another at the heart of it. Yes, at the heart of it, it's the atomic element and the atoms, and how the atoms are moving with each other, and how they will act on something else. So yes, it is at its essence from atomic bonds and the forces that are acting at the atomic level. I will show you soon. um,
So isn't that
okay,
like either the strong force or the weak force? Just out of curiosity.
so you're in the right arena. Um, Pretty soon you're going to see that the atomic forces that are at play here are actually electrical forces, but we won't ever really get to that. And yeah, so it's not. I don't think it's in the category of strong or weak, but it is in the category of the strong forces of the major forces, the four major forces that are there. Um, Actually, I should Google, or someone can Google really quickly, where does electrical forces lie under of the four major forces?
Isn't it electromagnetism? Or what's,
It,
oh,
I
is that
think
not
it's
a
a strong
force?
force. I think it's a strong force. Someone can Google this. Yeah, where does electrical force? What type of force is electrical force? There's like four major type, right? Strong, weak, nuclear, and I guess gravitational. I don't know. I don't think it's a weak force. I think it's a strong force. Someone Google. Someone Google.
I think
um,
electromagnetic is a elemental force.
so it's its own category. So then
Yeah,
it would be on that. Yeah.
Pretty sure it
it's
comes
like
So
from
static.
electrons, but I mean, I don't
Yeah, it's
like
movement of
that's
electrons. Yeah.
broad.
yeah, I'll look this up after class, but because we're going to talk about this a little bit tomorrow. So, yeah. Okay, can
So
uh-huh.
the bookshelf situation,
Yeah, I'm
I
about
don't
to,
understand what's going on with that.
yeah, give me a second. Let me get to the another question in the chat that has to do with the bookshelf, I think. Can we say the normal force will always be zero if the acceleration is zero? The normal force will always be zero if the acceleration is zero. I don't think so, because the normal force is being balanced out by another force. And in this situation, for example, the normal force here, n, let's say n equals 10 newtons, and I don't know, the gravitational force, something 9.8, right? So let's say 9.8 newtons. I'm just making that up. And the applied force is 0.2 newtons. So acceleration here is zero, but the normal force is actually a number, 10 newtons. So they have to balance each other out. Think about that and let me know if we can add to that. Okay, so we have our book now, and the bookshelf at a diagonal is applying a normal force that is perpendicular. And we traditionally still continue with our frame of reference being that xy, right? Which would be here. So in this situation, the normal force would have to break down into components, even though it is still perpendicularly out from the surface. So you have options here, right? Which color should we go with? Let's go red. So you could break this down into its components if you needed to, or sometimes, and you'll see this probably tomorrow, sometimes it might just be easier. Ooh, I've never used gray. Let's try gray. Oh, that's nice. Sometimes it'll be much nicer for you to just flip over your axis. And if you flip
So
over your axis, the normal will then be on the y.
so is this to say that like on that bookshelf, the normal force has an x and a y component rather than just a y component on a normal
Yes,
bookshelf?
yes, that is right. I
Which
want
means the book is going to fall to the ground.
Yes, if it doesn't have something like friction holding it up, then it's going to fall to the ground. But the point here is that the normal force, no matter what direction it's in, it is always perpendicular to the contact point between the two surfaces. It is always perpendicular, no matter which direction you draw anything. The normal force is always perpendicular. Okay, I think we're at a I think we should take a break, guys. I know you might not. Okay, 10 minutes. Let's come back at 12:15. You're already gone. Okay, let's come back at 12:15. I'll leave the summary on the slide. 12:15. Let's all come back.
Hi.
Hi. Hi, Randy. Hello, Owen. I see you too. I hope some of you, others of you, are slowly coming back. Hello, Daniela. I see you too.
Hello.
Hi. Hi, Sanjita. Hi, Robin. Okay, I'm glad some of you are back. Hi, Saja. I'm glad you're here too. Okay, and I see more of you. Brian and Andrea, welcome. Welcome, everyone. Hi, Mehmet, and you're back too. Hello. Hi, Luis. Hi, Mafar. I see your thumbs up too. Okay, so I thought we could spend the last few minutes of class. I'll show you these two slides tomorrow. In fact, it'll be where we start. But I thought we could spend the last few minutes with an actual tension problem so that we could get, some practice here, see how it goes. Okay, so we're back in it. Newton's second law. Here we go. Lots of tension. A traffic light weighing 122 newtons hangs from a cable tied to two other cables fastened to a support as in the figure. The upper cables make angles of theta equals 37 degrees and theta equals 53 degrees with the horizontal. These upper cables are not strong as the vertical cable and will break if the tension in them exceeds 100 newtons. Okay. Does the traffic light remain hanging in the situation, or will one of these cables break? So the traffic light weighs 122 newtons, right? So the weight of this is 122 newtons. Oh, I still have the gray. I never tried the gray. I think it's okay. It hangs, actually, let me go to pink. We see the angles 37 degrees here and 53 degrees here. Okay. Okay, and it says that the upper cables cannot exceed a tension of 100 newtons. So tension 1 plus tension 2 in total cannot equal 100 newtons or more than. So we want to see if this will break or not. Now, for us to analyze this, remember this is all about perspective. So our goal is to look at the situation and figure out eventually what is T1 and T2. Everything acting on this knot right here is T1, T2, and T3. But additionally, we have this traffic light here that is being acted on by T3, right? So we have two objects here, technically. The knot here and the traffic light. So we can separate these two into free body diagrams and take this drawing over to the other side and we'll see what we have. Let's start with the traffic light because the only thing acting on the traffic light is the tension of this rope hanging up, right? So we know here that this is going to be a tension 3 acting away from the object and parallel to the rope. So let's take that to the other side. Okay, and so that's what we see here. You can model this again. You can draw this as a dot, right? A dot with tension 3. This is the cable acting away from the object. The object here is the traffic light. And we also know that the force of gravity is acting on the traffic light. So we have these two vectors, forces acting on the traffic light. So that's a start. We can write Newton's law of motion for just this first situation, just to keep things simple. Nothing is acting in the x direction, and the only thing here is forces acting on the y direction. So we can start again with Newton's second law, F equals ma, and we want to do it for this first situation only in the y direction. Let us see what we get here. Okay, so the sum of the forces in the y here are equal to 0 because we are assuming that the traffic light is hanging, it is not falling, and nothing is acting on it, so nothing is making it move. So the sum of the forces in the y for the light is equal to 0. Now let's sum up the forces, right? The sum of the forces then come directly from the free body diagram. So this comes directly from the free body diagram, and we see that the tension is acting upward and the gravity is acting downward. So T3 minus Fg, and this whole thing is equal to 0. Now, mathematically, we can just move things around, right? So in this situation, we have figured out one variable already, one of our tensions. Tension 3 is equal to the force of gravity. Okay, we can't go any further with this equation and with this free body diagram. We've done everything we can. We can now move down to the knot. Remember that this knot is where the three cables meet. It's this knot right here. So this is also, uh-huh.
So this means there's like a tension vector of a positive of a y and an x component, like for each.
Yeah, that's right. So if we look at the knot and the perspective of the knot being the object, we see that the cable for T1 is acting away from the object parallel to. The tension from cable 2 is away from the object, also parallel to the rope. And tension 3 will be acting away from the object, also parallel to the rope. The object here is the knot. Okay, and just like Randy told us, we can break these up because we are only going to sum up in the X and in the Y. So we're going to need the X component of T2 and the Y component of T2. We are also going to need the X component of T1 and the Y component of T1. If it helps, you could even draw these as other arrows. I suggest a different color, but it's up to you. You could even draw these as other arrows just so you can see that you're only adding on the X and Y axis. Okay, this is a lot to add up in the X component, 2 to add up in the X, and 3 to add up in the Y. You can do Newton's second law for this, no problem. Here's another way of organizing this. You can also draw out a table. So here are all of the table, all of the forces that are acting on it, and we can get the X and Y component of each. And this is only for organization. So if we look at the tension on cable 1, the X component is minus T1 cosine theta because this is acting in the negative direction here. Minus is the direction and T1 cosine theta is the magnitude. It's acting in the positive Y, which is T1 sine theta, and that's what we have here. If we look at cable 2, it's acting in the positive X direction, right? So that's T2 cosine theta, and in the positive Y direction, so T2 sine theta. Now, if we look at the tension in cable 3, there is no direction in the X. There's no component, so that's 0. And in the Y component, the magnitude of it is just T3 going down. So negative T3, and based on the first equation, we know that T3 is equal to the force of gravity. So we can write negative Fg. So now we can write our Newton's laws of motion for the knot in the X direction and in the Y direction. And so in the X direction, the sum of the forces equals 0. There's no acceleration. And in the Y direction, the sum of the forces also equals 0. There's no acceleration there. And so now we can just add across, right? Minus T1 cosine theta 1 is the X component of T1, T1X. And T2 cosine theta is the X component of cable 2. And that's this whole section right here. If you wanted to just skip to the sum of the forces, you could do that. The table is just for organization. And so for the sum of the forces in the Y, we see the same thing, right? T1 sine theta 1 is T1 Y component plus T2 Y component plus T3 Y component, which is the only one, Fg. And now you have your equations, right? Now, up until this point, the physics is done. Our goal is now to figure out what is the sum of T1 plus T2 and does it exceed 100? So we need to solve for T1 and T2. And we have here 2 equations and 2 unknowns. So we can solve one equation for one of the unknowns and plug it into the other one and then plug in our variables from the problem. The order that you do it in depends on whatever is comfortable with you, and you really want to just do what's simplest. So I think what they did is solve for T2 first from this first equation. So we're going to solve for T2 on this first equation and then plug it into the T2 here. I think that's what they did. Let's see. Um, okay, so this is the first equation, and we solve for T2. Yeah, they're going to solve for T2. And this is now the solution for T2. And now we're going to take that and plug it into the second equation, because we don't know what T1 is, right? We don't know that. So we can't do anything with it, but just plug it in. So now we plug it into the second equation. This T2 is going to be plugged in there. And so you see it here. The first part, T1 times what is now T2, and times the sine theta 2 continues, and minus FG, and minus FG here is equal to 0. Um, Again, now it's all math. The first thing you might want to write here or summarize is that this sine theta over cosine theta, anyone?
Tangent.
Thank you. Yeah, this is a tangent theta, right? So that we can make that into a tangent theta. Then you can pull out the T1s. You can pull out this T1 and it'll be T1 times, in parentheses, sine theta 1 cosine plus cosine theta 1 times tangent theta, and the whole thing minus FG equal to 0. So now we just solve for T1. And so there it is. This was the whole component up here where we took out the T1s, right? We isolated the T1 and we brought the FG over to the other side. So that's why it's positive. Now that we have this value of T1, we can calculate the force of gravity because we were given, I think, the mass. I think we were given the mass or the weight of the light. We know the angle theta 1 and theta 2 given to us also. And so we can plug those in. Yeah, they gave us 122 newtons as the weight. The angles theta 1 and theta 2. Now, these angles are just kind of being told to you that they are the equivalent angles that you would see here, right? You just want to confirm that to yourself, that they are the right angles, but they are. Usually the problem will give that to you, or you have to solve for the angle first and then go through the problem. So I would just get comfortable with your angles and being able to draw, what is that called? The triangle that's the same? Congruent? No? I don't know if that's the word, but an equivalent triangle just somewhere else. And eventually you'll get to a point where you can figure out which angles are which. Don't just assume that they're equal. Like, go through.
Equilateral, is it?
Or equilateral. Is it equilateral? I think so.
But like,
Well, the
if
sides
they're
are
alternate
equal.
interior and they're parallel, then that is equal.
Ah, okay. Yeah. So those are the rules you want to remember. If you don't remember them, you can draw it out on paper. That's what I do because I don't remember the rules and I just keep flipping the triangle around until I get there and convince myself that they are in fact equal. So in this case, they very nicely gave it to us, theta 1 and theta 2, right? So now we have the value for tension 1, and we can plug this into our equation for tension 2, right? This is T1 right here. We plug it in, and we now get a value for tension 2. And so now we can see, will either cable be more than 100 newtons? No, neither cable will be more than 100 newtons, so the cables will not break. We're okay here. But this is how you solve for the tension 1, for the tensions in cables. We have solved for tension 1, tension 2, and notice that there was no need to numerically solve out for tension 3. We just know that it's the force of gravity, right? Which is 122 newtons. So this is a typical tension problem. This part is all math. This is all the physics. Any questions?
Could you go back to the other slide? The last one.
Okay, so I hear no questions, and it's about to be 12:30. So I think what I'd like to do now is take a few minutes to show you guys the lab. The lab is all about drawing free body diagrams in everyday life, what you see out in the world. So you will draw the free body diagram using the forces that we've learned so far, and do that for 3 different scenarios. And I give you on the lab that I'm about to publish a guide to the different forces that you could use and how they're drawn, and also a sample, a sample of free body diagrams. So if it's okay with y'all, I'd like to switch over now to that. Okay. I hear no.
I object.
Oh, I heard it. I heard an objection. And it's canceled or neutralized by Mehmet's thumb. So now we're in neutral space. Okay, so let me show you guys the lab. It should be publishable now, and let me go into student mode and show you. So if you don't see the lab, refresh your canvas right now and you should be able to see it. And I will take you to it on the screen right now too. Okay, let us go to it. Okay, so I hope this is large enough to see also. So here's our Canvas page. And now if you go to our chapter 5, you can go to the FBD at home, free body diagram at home. And I hope this should work. Okay, let me make this large so we can see
So
it.
this is lab 4, right?
The 4th assigned lab, yeah. Okay, so free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting on an object in a given situation. Some examples are going to be shown to you in this guide. Take a look around you and identify and draw the free body diagram for 3 situations around you. We will use free body diagrams in problem solving to resolve forces into X and Y components to solve for the unknowns. So let us look at our guide really quickly, and then we'll look at samples. Let's see if this is large enough. It's so much faster when I just download them.
Oh my God, there's people and they're real and they're at campus.
Really? Oh, you can
Yeah.
see the picture? I can't see the picture. Okay.
Wow, I haven't seen that in a long time.
Okay, I'm gonna show you guys right now what what Randy is seeing. Okay.
I almost don't believe it.
I'm with you. So let me show you the guide first, and then yeah, I don't believe it either.
I should have taken more pictures at school because they could have gotten me through, you know,
Yeah,
these hard times.
did I tell you guys that, or did I tell my last class? But everyone used to talk, well, all the other instructors would make so many, you know, comments about me taking pictures all the time of them, of me, of students. Like, I just love, and I don't even post them. I don't show them to anyone. They're just, I don't know. Anyways, but now,
Paparazzi.
yes, now I have pictures forever to use when I need. Okay, so here is your guide to the free body diagram. So take a look at this one document here, and it's on the lab. It tells you a little bit about free body diagrams, and then it splits up the forces and shows you examples of how to draw them for different scenarios. It'll tell you about the gravity force, the normal force. Again, here they put F sub n. You could use capital N, a little n. Notice it's always going to be perpendicular, even if it's slanted. Tomorrow, I think we will have time to go over the frictional forces. And so you can start to see that here. And then applied forces. We don't have tension, but we have a good definition of tension in our slide set and in our book. So this is just the guide of the different forces and how to kind of draw them on an object, on a dot. So if you need a definition of one, look in the guide first. This will help you there. Now here's the actual assignment of what you're going to do. Let me switch the share to that one. Okay, so this is the free body, give me a second, there it is. This is our free body diagram assignment at home, and you will do this for 3 different scenarios also. It says, draw a free body diagram for objects that you see around you. Include a picture, include a description, and the free body diagram for 3 objects. Practice physics from a safe distance, no matter where you are when you're taking these pictures or whatever you do. So here's example 1. Description of the object, a funny book on the table. And if you were to actually zoom in, I think, I'm gonna physically zoom in. I think it says the wine chemistry. I think I was at a coffee shop.
Yeah.
Yeah, I was at a coffee shop in Torrance, and the people next to me were studying, and that's what they were studying, wine chemistry. And I took a picture of it because I thought it was funny. Okay, so here is the book, right? The book is the object. In the description, I know what the object is. It's the book. So I draw the point here. I draw the point here. Yeah, funny things. I draw the point here with a normal force acting on it from the table and the force of gravity acting on the book also, and it's also the weight. Notice the things that are in the free body diagram. First, it's a dot or a square, and the vectors are centered at the dot or the square. 2, the vector is a line with an arrow. The force is labeled as a vector, and I can clearly tell what is the force due to the notation, the subscript. And the same here, the force of gravity also equal to the weight. So you have arrows and direction for the vector, you have vector notation on the force, and you can identify what is the force. Okay, let's look at our second example. Oh, okay. I don't want to give away the third one just yet. Okay, object 2, people doing funny things. These are students. It was it was the last class doing funny things. What they were doing was actually physically measuring the letters at the top of the building. That was a lab. We'll do that in the future. Okay, people doing funny things. So a person, and here I put in italics, the person is walking towards the LATCC letters. So here's the person as the object. They have a normal force acting on them and a gravitational force acting on them. And because they're walking and pushing themselves, I'm not going to use a frictional force. I put an applied force because they're moving forward, they're walking. And the walking part implies that there is a net acceleration here. And so that's what you see here. Okay, our last one. Oh my God, that's me. I'll show you guys. Okay, that's as big as it's gonna get, I guess. Okay, a funny hat on some lady. I am that lady. Guys, this was literally 4 weeks before the shutdown. 4 weeks before the pandemic, February 2020. No, Owen, that is not in Guatemala. This is in Mexico. But I have a picture of pyramids in Guatemala too. I'll share that another day. Yeah, this was in Cancun, right? Cancun, yeah. Yeah, I went during the 3-day weekend in February. Oh yeah, you should go. You should definitely go to Petén. Yeah, Tikal is where all the pyramids are. Okay, so the funny lady and the object is the hat. The hat on this funny lady, that is I. And I put an asterisk again, the wind is blowing to the left. Okay, so here's our free body diagram, a dot, and in the vertical, we see the normal force from my hair contacting the hat or my head, and the gravitational force that's acting down on the hat. To the right, we're going to have a frictional force that we don't know of yet, but you will. The frictional force
Is that like your hair? Is that like your hair on the hat?
Yeah, it's what's holding my hat from blowing away from the wind. I probably should have started with the wind. The wind is blowing to the left, so I have a force due to air, right? I can move that closer. A force due to air moving to the left, but my hat is not moving. Because it is not moving, there must be a force acting against the wind. And what's holding it to me is the friction from my hair, my head, to the hat. So it's a frictional force, and this little s stands for static frictional force, which means a frictional force that exists, but the motion of the object is still static. You can have a frictional force that exists when the object is moving. That's a kinetic, and it'll be a sub k. And that's, for example, when you're walking and the frictional force on your shoes, or when you're driving and the tire is moving, that's experiencing a frictional force on the ground too. So have fun with this. Pick 3 objects that show some sort of movement. Show the forces that we have worked on so far. Applied force, gravitational force, normal force. Uh-oh, I can't put the other finger up. Tension. And tomorrow you will see friction. So if you wait for tomorrow, you can include a frictional force also. Any questions? Oh, Gary, I don't think you were with us on the first day. So yeah, I'm from Guatemala too. Okay, just to make sure, any circular motion from chapter 6 is going to be on the next exam. No, nothing from chapter 6, but the circular motion that's included in chapter 4 for centripetal acceleration will be included. Anything beyond that, no. So if I do the lab today, I don't have to include friction, right? You don't. No, I'll say no, but you should, for your own benefit. Let's see. Yeah. So include all 5 forces. I actually was going to say, you guys, they don't all have to be in one scenario. They can be throughout everything. That's fine.
What are all of the 5 forces again?
Let's see if I can write them on here really quickly for you guys. We have an applied force, F sub G. We have, oh hell, that's not applied. F applied. Gravitational force, or gorge, whatever. Oh my God. F sub G. We have a normal force. Oh God. Tension. Oh God, I don't know what's happening. It's because I'm angled at a weird way to my keyboard. Tension, and then frictional forces. Oh Lord, here we go. It's either going to be F sub S or F sub K.
Okay. Okay. Thank you.
Nathan said, I noticed in the previous lab there are questions on forces. I thought I took those out. The example should be on forces, but there shouldn't be questions on forces. But if there are, perhaps now it would be a little easier to solve them. I thought I took them out, but if I didn't, now we are equipped to solve them. So solve away. Okay, any other comments, questions? Okay, I'm going to stop sharing the screen. Oh no, I have questions. Okay, I'll leave the forces up on the screen. Also, when it's asking for acceleration, I'm having difficulty understanding which type of acceleration it's asking for. Oh, okay, it depends on what the question says. Okay, and if it says total acceleration, then you'll have to, and there's a circular motion in the problem, then you'll have to add up the tangential and the radial. If it says, just what is the acceleration and there's nothing moving about a circle, it's the general acceleration that we're working with. You just want to make sure beforehand if you're moving in a circle or not. If you're moving in a circle and it asks for this acceleration while it's in motion in the circle, that'll be a centripetal acceleration. If you have a specific question, I can help you through that one. Okay, I'm going to stop sharing, and I think I'm gonna stay on the call, but I will stop recording, and stay on for any specific questions from anyone. But I think we're officially done for today. So thank you all, and I will see you tomorrow. Tomorrow we will go over frictional forces, and we will have about 3 to 5 practice problems to get us ready for the exam. Yeah. Okay, bye everyone.
Thank you, Professor. Have a good
Thank you,
one.
Jan. Bye guys. Bye everyone. Bye Gary.
Bye.
Bye Sanjita. Bye. Bye Robin. Bye Mehmet. Bye Owen. Bye Luis. Bye Daniela. Bye guys. Yeah, Nathan, stay on if you have more questions. I'm happy to help. Bye Esmeralda. You have a good day too. Bye Vafar. Bye Andrea. Okay guys, I think I'm officially gonna hit stop recording.